We'll start with Ivan talking about reactive programming and Qt. So please welcome him.
Thank you. First, before I start with anything, why am I here? I'm a KDE developer for quite a long time, and apart from that, I've been giving talks and I'm teaching C++. And I'm a functional programming enthusiast, which is to make a big difference between a functional programming enthusiast and a purist. I'm not going to talk about any category theory stuff or anything similar. I'll try to be as concrete and as practical as possible. So first, disclaimer, one of my favorite quotes by Philip Wadla, that you should write your code as if the people who are going to read it are psychopaths and that they know where you're located at. This doesn't mean that you should write code that everybody will understand, like when object-oriented programming came to existence, nobody understood what objects are, but people started using new stuff. So this is not excuse to cater to developers who don't want to learn the language that they're using. Because I always, after my talks, I always get questions, but nobody would understand the code if I wrote it in that way. And this is the disclaimer so that I stop those kind of questions. And the last disclaimer is that the code on the slides is optimized for the slides and not actually a production code. So first, what is reactive? If you go to the Reactive Manifesto webpage, you'll get a huge block of text, which is something, something resilient, something elastic, something, which is essentially buzzwords. And it's marketing buzzwords created by the people who are trying to popularize reactive programming. Unfortunately, I don't think that's the way to do it, at least not to the developers. Now, second try, if the original website is not good enough, let's search the word reactive in Oxford Dictionary. And it says it's showing a response to a stimulus. Unlike proactive, which means I actually want you to do something for me. So when you're proactive, you ask for something, and when you're reactive, you just wait for somebody to send you a message. In programming, you can see stuff that are used for reacting. For example, event callbacks, Java event listeners, Qt signals and slots, and similar stuff. And somebody could even say that I/O in C++ is reactive because it reacts. When you type something and press enter, your code continues working. But usually when you want to say reactive, you mean reactive in a way that doesn't block the main program, unlike the I/O. So apart from actually reacting, it's a nice idea, but what do you use it for? So the idea is to separate your program into separate components, and each component should be independent of the other. And the components ideally should not even know that the other ones exist. You should try to make small containers that do just the thing that they are supposed to be doing. In Qt, we have had some form of reactive for a long, long time, since Qt 1. So we had signals and slots. You were able to connect a message sent by one component with some kind of listener. And for example, a button doesn't need to know that a mouse exists. Button doesn't need to know that it will be used to close a window. It doesn't need to know that a window is something that exists in the real life. You need to design the components like the button so that they can be used on their own with in different purposes. Now the Qt connection mechanism is a little bit limiting. The only thing that you can actually do with the message that has been sent is, for example, skip a couple of arguments. There is nothing more advanced that you can do with a message. And usually, when you have completely separate entities, they don't actually need to speak the same language. Sometimes you need to translate that message to another format or something else and pass it on. After signals and slots, QML came into existence with the idea to create everything in a declarative manner. And then you get, again, a nice syntax for creating signals and slots. But in this case, you were actually able to do something more than just forget a few arguments. In this example, which is completely useless, but it shows the point. For example, when mouse sends the event that the epsilon coordinate has changed, your code will automatically calculate what the height of this rectangle should be. And this is the idea of the functional reactive programming, like it says in the title. The idea is that you have a message and you can transform it in any way that you want before it reaches the actual receiver. Now QML is all and great, and everything is declarative. But if everything is declarative, how do we end up with code that is full of state and full of if-thens and everything else? Obviously, the UI is declared in a declarative way, but all the logic tends to be just really, really bad JavaScript. Instead, the idea is really to organize your code as a data flow. You have sources of information, you do something with those, and you have the receivers in the end. So now let's forget about signals and slots and everything else. We want to create something that will abstract over any kind of asynchronous operation, be it a UI stuff or handling different threads or distributed processes or everything else. We want to create something that will be simple and able to handle all of these different use cases where asynchrony is needed. First, one of the main ideas in functional programming is to limit the states your code can be in. One of the nice blog posts from John Carmack of the Doom fame and Quake fame was about functional programming in C++, and the idea that most bugs that you have are coming from the developers, not say your, inability to handle state. So we as the developers cannot handle all the states that our applications can be in. And when you add multi-threading or any kind of asynchronous operations, it just becomes even worse. And then we are trying to fix it with, obviously, if you want to use threads, you start using QThread or POSIX threads or anything else. And you, because you're a cool developer, you go the lowest level that you can find. So it's POSIX threads and, let's skip this, and mutexes. One of the best comments about mutexes that I've ever seen is by David Butenhoff. He said that we shouldn't have called mutex as a short, cute acronym of mutual exclusion, whatever. It should be called a bottleneck. Because when you say, OK, I'm going to add a bottleneck to this part of the code, you know exactly what you're doing. Bottlenecks are sometimes necessary. You need synchronization at some point, but you don't actually, you know that it's a bad thing. And when it's called with a cute name like mutex, then you can throw a lot of mutexes in your code and nobody will complain. So the idea is somehow to manage to organize your code so that you have as least synchronization as possible. For that, you should use something that looks like a future. Do we all know what a future is? Cool. So we have in the standard library from the C++11 stud future, we have boost future, which is much better. We have QFuture, which is not something I'm going to comment. And Folly Future, which is, I guess, the best of all four. Folly is a Facebook C++ library. It is not used anywhere apart from Facebook, but at least this class is really nicely implemented. So the problem with the usual futures, if you want to call something that returns you an std future, the only way you can get actually the result is by calling the .get method. There is still not a .then where you pass a continuation or anything else. And when you call a .get, you actually block your main program, or you block the caller until the future arrives. And that's bad because you just killed a synchronous operation because you called a synchronous .get. Instead, you should use futures that have .then, and just when the result appears, the future itself will call the handler for that result. std future is going to get .then. It should be in C++ 17. Jens might correct me if I'm wrong. So if not, at least you can use boost future if you don't use C++ 17. And what would the code look like if you actually used continuations? Just imagine you have a library that retrieves a web page, and then you say .then. When the result is there, you do something with the result. Or if you have something more to do, you can get a lot of images from that page, and then again call some continuation when each of those images arrives. If you want to compose the futures before the await arrives to C++, you can do something like this. You can check out my talk, Monads in Chains from Meeting C++, and this is a shameless plug for both myself and Meeting C++. But we don't want to be imperative today. We want to talk about purely functional reactive programming instead of just writing imperative code that handles asynchronous execution well. So in order to understand what a functional reactive programming is, we first need to cover, again, one of the features that C++ 17 is supposed to have in some way or another. And currently it's available as a separate library called range v3, and it also, similar one exists in the boost called boost.range. So in STL we have a couple of nice algorithms, so instead of writing dull for loops which tend to become huge, you should always write something like std accumulate if you want to sum all the items in a list. If you want to, instead of doing the sum, if you want to make a product of those, you can do something like, again, std accumulate, but pass it a custom functor that will just multiply the numbers. But what happens if you actually don't want to do the same on the actual values in your collection? You want to make some kind of transformation. In this case, we want to square each of the elements and then sum them up. Then you're a little bit in a problem. So we want to do something that is like this in Haskell. If you want to actually perform a transformation on a list, you either have to destroy the original list to save all the results that you got in between, or you need to allocate more memory for the normal STL. And then you would transform the original, you would create the squares and then accumulate, which is definitely not efficient. And the code looks even uglier than the code we started with. Instead of, you should, from today on, start using at least one of the range libraries. And you would be able to do something like accumulate, pass all x's through the transformation of squaring them. And then when they pass through, they will be summed. The good thing about this is that it doesn't actually create any intermediary lists or vectors or whatever. It just provides a view on the data, original data, that is squared and then some magical iterators go through the collection and everything is summed. So the ranges are one of the coolest things that are planned for the C++ 17, as from my point of view at least. You can even do something like SQL, or .NET people would call it link, and all functional programmers would know that link is not anything new. It already existed in all the functional programming languages that were ever invented. You can have a collection of transactions, then filter them out for the price range, then group them by, then sort, or anything else. And the code would actually look quite similar to what SQL looks like. And it would be much cleaner than if you did this in a manual loop. And apart from it looks much cleaner, it's much more easier to change. If you just want to remove the filter, you remove one line or comment it out. And if you created a huge for loop, you would have problems to think in which places I actually do the filtering. So this is one of the things that I'm trying to popularize regardless of this talk. So please start using something like ranges. It's a really cool thing that will make your code much more clean to write, to read, and you won't have any surprising bugs in it. Okay. Not important. So now, when we know what futures are, we know what ranges are, we want to learn what are streams. And not streams in the sense of I/O streams, but streams in the sense of reactive programming. So the idea is that, let's skip. We have a future, and a single future can return a single value. If we wanted to return a list, we would have a future that needs to calculate the whole list and then return the whole list, which is definitely not something that we want to do. If I move the mouse, I want all those events to be sent one by one to the receiver and not to wait for all the mouse events to collect a huge list and then send it to whoever is listening to. So we want to create something that is a stream instead, and it can call the .then method multiple times, not only once. From the point of view of the abstraction, there is not much difference between a future and a stream. Because when we said, what is a future can be anything with a .then method, we didn't say that the method that you pass will be called only once. So essentially the same abstraction that is used for a future can be used for the streams as well. Question for the audience, what is the difference? This is my favorite question always. What's the difference between these two? And don't try to find some low-level differences because they obviously exist. Something really huge. Okay, next one. Okay, next one. So try to read the title of the slide. So obviously, all those were correct answers. The thing that I wanted, the point of this slide was that it doesn't say std for each. You can define for each for anything that you want. So it can be something that even sums and doesn't do what range for does. And range for is unfortunately strictly defined as a for loop with iterators to begin and blah, blah. And if you write for each item something, because of the argument-dependent lookup, whatever the class items is the instance of, it will do something for that class. So for the stream, would I be able to write range for and pass x for all x's in a stream? Stream as a reactive stream, so something that sends events. At this point in time, it won't be possible. Why? Because you need an iterator to the beginning and an iterator to the end. Do you know an iterator to the end for a asynchronous stream? You don't. Do you know even the iterator to the beginning of an asynchronous stream? You don't, because you might still not have the first item in the stream. Unlike that, you can define a for each algorithm that will work on streams, and it will be as simple as just calling stream.then and pass whatever is passed in whatever lambda you pass in the for each. So this could properly be written like for each stream, comma, some lambda. And it would work unlike the range for. And that's the idea of why the generic programming and algorithms in STL are so important. Because for different collections and different types of things, you can define your own. And they will be called instead of the standard ones. Okay, we already saw that. So what can be modeled as streams? Obviously the UI. When you type, you send events. When you move the mouse, you send events. Whatever you do in the UI, you send some kind of event. You can use it for implementing web services. You can use it when you're accessing a database. The database can just, you send it a query, and whenever it calculates a new result, it just pings you, instead of blocking your program until the next result in the database is available. And unfortunately, I don't think that C++ there are libraries for reactive access to SQL, but it should be possible to implement because other languages do have it. So any type of callback you can convert to streams. Any signal slot stuff from Qt you can convert to streams. Even normal data collections like vector, it's still a reactive stream in a sort. Because what's the difference? The vector is a stream that whose all elements are currently available. So it doesn't make any problems to consider all the usual collections in STL to be streams like the real streams are. And this is one of the points why the abstraction is a great one, because it doesn't really cover only the things that we wanted it to cover. It covers a little bit more stuff. Everything that looks like a stream is a stream. Like in Doctor Who, everything that contains an image of a weeping angel is a weeping angel, right? Okay, so the only problem with streams that make them different from regular collections is the fact that you can apply only the transformations that are for input ranges. Input ranges, so something that you know the current element and you can reach the next one. You don't know the end, you don't know anything, so you can't sort them. You can't use partition, you can't use a stable partition on anything else. You always need to use just the algorithms that can work on input ranges. So we are going to start with a small demo. So we have a mouse in our window, and we will convert that mouse somehow to a stream of events, and we'll pass all those events to a move to method of something that is called mouse cursor. So this is a very weird syntax for just making connect something to something, right? And don't be afraid of the star in between. It's actually something a little bit uglier, but I wanted to hide it. So when I move the mouse, trivial things happens. So you see a red rounded rectangle that moves along with the mouse. It's trivial, right? And again, one of the things that is cool with this is that, like the new slot and signal syntax in Qt5, this is type checked at compile time. But this is crap, right? If this is the only thing that you can do with reactive streams, I wouldn't make this presentation. So the next thing, we don't want that rectangle to follow us all the time. We want, for example, to make the rulers as you have in the drawing applications. You move the mouse and it shows on which x coordinate and epsilon coordinate you are. So instead of moving the cursor, we want first to pass all the events from the stream through some kind of transformation. In this sense, the transformation will be x projection on the x-axis, which is in essence just, okay, forget the x and forget the epsilon, place it to be 0, and leave the x as it were. This is fun because it's a multi-screen. So when I move the mouse now, the green dot stays at the top of the window and nothing else happens. It just follows the x coordinate of the original thing. But now you can complain, okay, formerly we had a cursor and now we don't have the cursor but have something completely else. We want now to somehow to make it so that the both things work. Obviously, we could have just said make stream of mouse connect to this, make stream mouse connect to something else, which would be bad. Instead, you can create your own type of algorithms, something that will behave like T in Unix shell. So just swallow all the events and pass it to whatever is inside T, and then continue sending those events to everything that is afterwards. So this code, what does it say? We are creating a stream. We are sending its data to a mouse cursor move to. And apart from that, we are going through a transformation that just takes the x coordinate and passes it on to top ruler marker move to. As I said, it's not a star operator, it's something much uglier. So the current implementation uses this syntax because this is what a bind operator in Haskell looks like. The final one will use the bars like the regular ranges. That's the reason why I hid it behind a star, because it's not a bar yet, but it's going to be a bar at some point. And what will this code do? Oh, for the love of God. Okay. So when I move the mouse, the red rectangle moves, the green rectangle moves, the green dot moves as well. But obviously it's not enough. We need to have the second ruler as well. If you don't like, for example, the syntax of TEE, you can use something that's called parallel or fork or whatever you want to call it. The TEE thing is mostly used for debugging and not actually for forking stuff. You just can, it's like a listening device. You can tap a phone line just to listen what is being said at that point, and then you can push a QDebug or something else. So this version of the code I don't need to run, but it's obvious it will have left ruler, it will have the top ruler, and the inner red square. But still, it's kind of boring, right? Now, we kind of created something more complex than we used to have, but still not enough. And does anybody care about the implementation of How would you do similar things to this? Huh, somebody actually nodded. Okay, so the first thing, because of the bind operator, we needed to create a namespace called stream, so that afterwards, when anything that is cast to something that belongs to the stream, due to ADL, it will call the bind operator will just call .then and pass it a continuation. Now, in this case, you would probably use a perfect forwarding over there and blah, blah, blah. But as I said, the slides are optimized for the slides and not for the production code. And the cool thing is that compiler will unwrap it most of the time, so you won't even have any calls to the bind operator in the assembly code. What does a map do? Map is synonymous to std transform. So whatever it gets, it applies a function f and passes it on. Is that okay? Is this part understandable? So let's try again. You create an object called map continuation. It doesn't matter. It gets a function f, which should be used to transform the message, and it gets to whom the message should be sent to. How does it do? Do it when its operator parenthesis is called. It will be called with a message, and then it applies f, the message transformation to it, and then passes it to the C, which is continuation. Is it all right? And how would you do T and fork? Again, it's quite simple. You can use Variadic templates for the parallel. You can pass how many continuations you want. And in each of the instantiation of the Variadics, you just call the continuation with the thing that you got and call the same operator of the superclass, which is the tail of the Variadic template stuff. So Variadic templates have quite an ugly syntax, but once you get used to writing code like this, it will be much more easier to grasp. And now we come to a huge problem in functional land. We don't want to have state, at least we don't want to have mutable state. Usually when people talk about functional programming, they think about pure functional languages like Haskell, where you don't have a single variable with multiple different values. You always have just a value. You can name the value, but you cannot change what that name represents. You cannot increase a value or anything else. But since we are not purists here, we want to have states sometimes. And we want to create something that will be more fun than the things that we had before. So apart from all the items that we had in the previous slides, we now want to add something called gravity object. What will the gravity object do? Whenever you move the mouse, the object tries to follow the mouse. It tries to get as close as possible. In order to achieve something like this, you actually need to have the state. You need to remember the previous position of that object. And that state will be changed with each mouse move. And we said that, well, John Carmack said that having a mutable state in a multi-threaded thingy is really, really bad. Is this bad in this case? When is the state an evil thing? Is unmutable state evil? It's not. Is it a mutable state always bad? No, obviously. It's not bad if it's not shared. So mutable state is only bad if it's shared. And in this diagram shows that most of the time state is quite a nice thing. The problem is that usually we end up in the red square. So since we are not in the red square now, we are in Berlin, we are in the green one. So we have a mutable state, but it's not shared with anybody. It is just used to process one single stream of data. Is it cool? So it's definitely not evil to be able to do something like we did with the gravity object. So the next object that we want to create we want to create a method called filter, which will just be used to ignore some events. In normal cases, you would filter on type of event or something else, just listen to the events that you're interested in. In this case, because this is a demo, we are going to have a really simple filter. Just let me jump to it. So we are going to filter all the events that are not, whose epsilon coordinate is not divisible by 100. So we will pass only the events when epsilon reaches 0, 100, 200, and etc. And you see the cross here. It sometimes jumps to the coordinate. Is it visible? And now somebody should notice a bug. What is the bug? In what sense? Okay, so while moving the mouse, it sometimes doesn't jump, and it should. This happens because, obviously, not all the mouse events exist. The mouse will, in reality, jump from one place to another, and if you didn't hit the exact epsilon divisible by 100, it will just be ignored. So in order to fix the last, I think it should be the last issue, you can create something that is not just transforming the messages or filtering them out. You can actually, for each message that you receive, you can create a transformation that will generate a lot more messages in between. So in order to do something like that, we could use a method called Flatmap. If we have a map, and you know it's std transform, what does Flatmap do? For each message it receives, the method that is inside can generate a lot of events, and Flatmap will just flatten them out and pretend that they are part of the original stream. Is it okay? We'll see the implementation. This is actually a fake Flatmap, but it's a simpler version. So instead of, just imagine a method that converts a vector of vectors into a vector of items. Just flattens everything out. Is it all right? And the 7th version. Now I can jump as quickly, I can move the mouse as quickly as I want. It always works because all the intermediary events are actually being generated, even if the system doesn't do it for you. So the point of it all is that, obviously, you wouldn't ever create an application like this one. That's the first. You wouldn't ever create this application with the streams, because you wouldn't create this application in the first place. But the idea is to point out that a lot of different behaviors can be achieved just by passing information through different transformations and connecting them to the other parts. Unfortunately, I haven't had the time before the conference to actually implement a serious application. I started, it will be an application for displaying presentation stuff, so PDFs with notes and similar things that will be able to communicate with a mobile phone, and then you can control it via events on your computer and everything else. And it will follow some of the rules that were popularized by Scott Myers. So it will have some features that will be really, really nice, but when that happens, I'll probably send a note or something like that. So this is something that can be used in much more serious applications than a stupid demo that you saw. It's actually something that is really popular in web services department. For example, in the good old days, Erlang was one of the biggest programming languages in the telecommunication. It was based on sending the events and everything else. It didn't have much more. Nowadays, a couple of different programming languages created libraries just like this one, so that you can use functional reactive programming in them, including Scala, Haskell, and quite a few more. Okay, for the fake flat map, you get an item, you call the transformation function. The transformation function will return some kind of collection, and then you will call boost for each to call the continuation for all of those items. It's nothing really smart. And something. Okay, so since in my other life I'm a teacher, I teach C++ to the students, I end up always with further reading. In this case, it's not only reading, it's also a couple of really nice presentations that you can find on YouTube. Okay, that's all from my side. Any questions? Thank you. Okay, so as far as readability goes, as I said, when objects were invented and you started to work with objects, nobody understood it. So it wasn't readable for a lot of developers. But then you start learning new stuff, and then it becomes natural to you. One of the cool things that Sean Parent said in one of his lectures, he saw a code in Chromium OS that was, I don't know, 50 lines long. It was used to find some panels and whatnot. And then he started analyzing the code and shortened it out to 2 lines of STL calls. And the patch was rejected because nobody will understand it. It's freaking 2 lines in the programming language that you are using, and you should know STL if you use C++, right? It's not C. It's not C with classes. It's a really powerful language. I don't claim that this is something that all the people in the world who are good C++ programmers will understand immediately. But after half an hour,
it's not a question about understanding, because as you said, half an hour of studying and I will understand. So the question is does it make it more readable than if I have maybe a little bit more code or a little bit more different code? Do you think this is superior, so to speak? And I'm asking all of
okay. I would say for me it is. Obviously, some people prefer loops. One of the claims that functional crowd is always claiming is that most of the time if you write a program in Haskell that compiles, 99% it will work correctly without bugs. So that's not an empty claim. The shorter your code is, the more that you rely on other people's bugless libraries, let's hope so, the less bugs you are able to make. So even if it was really hard to understand, I would rather go for a short code without bugs than for an easily understandable code that nobody will ever read because it's huge and nobody will fix the bugs that it has. So this is my personal preference.
And do you have an example maybe of an application that uses these kind of themes?
So a lot of recent, at least people who use Scala, they started to use a library called Akka. So I guess it's used in Twitter and LinkedIn, I think, uses Scala. I don't remember. So I don't have any specific projects at hand to show you, unfortunately, but I don't know. So I can continue with a lot of benefits that I think that this has, but let's cut it short and we can continue on the break afterwards. Mm-hmm.
Yeah, so this about operating the stream seems very similar to what shaded programs do for GPU programming.
Yeah.
So I guess that would be a good example in terms of how we parallelize stuff essentially when we use similar.
Okay. Although I wouldn't say that, so shaders is massive parallelization, and this is more concurrency that you don't need the same algorithm to parallelize over all data, but some things, but yeah, thank you. As easily as you would debug a huge for loop. In essence, first, you don't need to because it works as soon as it compiles, right? So when you see that something is wrong, then you have a chain. At least for me, I can't say that everybody will be able to debug it as easily. You don't need to actually run a debugger to debug this code. At least not for me. If you have thought in your mind, I want to make I don't know, fried chicken from a chicken. You have the steps how to process it, right? And if you forgot to remove the feathers, you will notice in the end, even if it's already fried. So it's kind of my approach to debugging functional programming, which is definitely probably not the popular one. I don't know, for me, it's much more easy to reason about how data flows and see where I might made a mistake. It's a huge problem to actually debug the library. But the code that you write in it, it's quite easy. Well, I would say any crash course on any functional programming language. Unfortunately, for C++, we still don't have a book called Functional Programming in C++. Maybe we will in a year or something. But the basic concepts could be learned from any other language, even from SQL, which is essentially the same thing with the uglier syntax, for me, uglier syntax. So if you, do you know Java? Okay, find a talk, it's called Scala for Java Developers by a hilarious Indian guy. Unfortunately, nobody knows the name of the guy, so he's still officially a hilarious Indian guy. And he has quite a few simple examples. It's not about streams, but how to do standard for loop stuff via maps, transforms, and everything. And if you grasp that, then going to streams will be quite easy. It's now the same thing, just asynchronous.
C++, as I know, is about object-oriented programming. I think that functional programming is a totally different thing. So even in your example, it wasn't anything object-oriented. Where would you still recommend object-oriented programming?
Okay, this is one of the things that I have a huge problem with. When anybody says C++ is an object-oriented language, my hair goes up, although it's now glued to my head. So I know. I wouldn't say that C++ is an object-oriented language. It started as C with classes, but then you get STL, which has almost non-virtual inheritance, virtual methods or anything, unless they want to make type erasure or whatever. So the exact library that you're using in the programming language is not really object-oriented. And if you want to hear an even more depressing view of object orientation in C++, you should find something by Stepanov, who actually created STL. He's the guy who hates object-oriented languages. And he hates objects, and he created your library. So I wouldn't say, if you are, obviously, Qt is heavily object-oriented. And in parts, it really sucks because of it. You should go for object orientation if you need it. You shouldn't create hierarchies over everything. A lot of things, a lot of polymorphism in C++ can be static during compile time, which will make your code faster and much less problems with it and everything else. So I don't agree with the premise of your question to be able to answer it. Well, I do agree. I love Haskell, so don't get me wrong. But sometimes I want my state changed. In practical C++ programs, the fact that it's imperative by design doesn't mean it's not functional as well. And now I'm going to elaborate what he said. So what is a functional programming? It's a programming language that has higher order functions. Again, you have in STL all the algorithms that receive higher order functions. Well, algorithms are higher order functions because they receive other functions and use them to do something. So I would say that C++ is a generic programming language. First, and afterwards you can call it object-oriented, imperative, even functional. And one side note, at this year's Central European Functional Programming Conference, there were 3 talks about C++. One talk about Haskell, 2 talks about something called clean, and 1 talk mentioned Erlang. So my conclusion was that C++ is the most famous and most used functional programming language. And all the speakers were invited, including myself. So we were invited to actually speak about C++ at the functional conference, which is weird. C++ can do a lot of functional stuff. It just doesn't have the same syntax sugar that Haskell has. And it will never have it, obviously. But there are other really ugly functional programming languages like Lisp, which is even worse than C++ for writing functional programs. Okay, I went a little bit overboard there, but it doesn't matter. And Scala, again, looks like Java with some things really nicely wrapped up. So Haskell is the prettiest, but it doesn't mean it's the only one. Yeah? Well, I try not to. Because I already am 5 minutes till the end, and just imagine if I explained everything that needs to be done here via method. Yeah. But when I said statical polymorphism, I actually meant template metaprograms. Yeah.
How to handle synchronization at the end of the streams? So if you have multiple streams, exactly the concurrent environment, and action at the end of the stream has to be somehow synchronized. How to handle it nicely?
In essence, you can connect a couple of streams to the same receiver, And since all the messages are safe and synchronized, your receiver will never be called from multiple threads. So that's the idea. If you want to synchronize exactly some parts of one stream and some parts of another, so that, for example, I don't have an example, but from time to time you want one stream to wait for the other. You'll have to just cache the result, the events that that have happened since the time that you want to synchronize. It would be much wiser if you were able to define your logic in a way that you don't need that synchronization. So one of the slides that I skipped, well, it is, but it's ugly. So, sorry. When you see a graph, just yell. Okay. So I guess most of you know what Amdahl's law is. The idea is if you want to make your code faster, you create a lot of threads and you create a lot of CPU cores. And then if you have 1,000 cores, your program will run 1,000 times faster. And that's the idea. It never works out because of the synchronization. If you have only 5% of your code synchronized or serial, then with 65,000 cores, 20 times performance. So anytime that you put a bottleneck in your code, you made it slower. I agree. And in that case, I would exit the pureness of functional reactive for that receiver. And then you can make it as complex and as ugly as you want. But still the logic will be as easy to debug as fried chicken. Okay, so the application that I'm working on, the presenter, is based on the idea that all Qt events should go through this part, and then you just, like you have a huge river, you make detours, what should go where, exactly like Qt does in its innards, but this will be explicitly done by the developer instead of having to connect to something to override event listeners or anything else.
I meant more in terms of with properties.
Okay.
You still have types in Haskell.
I have a stop, but let's pretend this is